Have you ever wondered why you don't slip out of the visually unpromising seats of Leviathan at Canada's Wonderland? Or maybe even when a toddler pushes his little Hot Wheel car on a little track up a loop-de-loop and the car reaches the top and doesn't fall right back down. It's weird to witness because you would think you'd fall right out of the roller coaster. But it's physics that keeps you in your seat the whole ride long. It may be a little hard to experiment with a huge roller coaster or a tiny car on a small track. So we present to you the spinning water-filled bucket. This example uses the same concepts as the roller coaster and Hot Wheels car, so it'll be easier demonstrating this weird phenomena when spinning it in a circle horizontally. Let's ask some questions and draw out some hypotheses. When the bucket of water is spun in a circle in the y-plane or horizontally, will the water spill out once it reaches the top, or will it stay inside the bucket? Confusing, right? Let's try it out. We first need to measure the mass of the bucket, which is 1.4 kilograms, and the length of the arm, 0.7 meters, which is the radius that we will be using in our calculation. We will also need the time it takes to spin the bucket, which will be taken with a stopwatch during the spin. All these we will need later on to explain using a specific calculation. It stayed in the bucket. Here's another example. Pay attention to the difference in this spin from the last.
3, 2, 1, go.
Again, it stayed in the bucket. I apologize for what I'm about to do next though. In fact, both scenarios that we talked about before the video are able to happen.
2, 1, go. Ooh.
Did I confuse you even more? Don't worry, I promise to explain everything, but let me prove it to you that both scenarios can happen. This second scenario may have made sense to you because gravity acts downwards and water will obviously move in that direction. But how did it manage to stay in the bucket? That was no camera trick.
Remember all those measurements we took? Those are going to help explain this physics phenomena. We will use a special calculation used for centripetal force. F is the force in newtons, which is equal to m, the mass, multiplied by a, the centripetal acceleration. The centripetal acceleration can also be written out as a velocity squared over radius. Centripetal force is the force that acts on an object when it is moving in a circular path. The force points to the center of the path no matter what the scenario is. To get the centripetal force in our first scenario, we must first find the velocity that will be plugged into the centripetal force equation. To do this, we simply need to divide the distance the bucket traveled over the time of the spin. Distance will be the circumference of the circle calculated by 2 pi r. The radius is the length of the arm. The time that was recorded is 83 seconds. The velocity is 5.3 meters per second. Plugging this into our centripetal force equation with all the known variables, we get the force. The same steps will be done to find out the other two scenarios' centripetal force. Time for the second spin was 163 seconds, and the time for the last spin was 2.2 seconds. The centripetal forces for all three scenarios respectively are 56.2 newtons, 14.6 newtons, and 9.7 newtons. Another important calculation for the force of gravity was that the water has. This will help us identify why the water did and didn't spill out of the bucket. Fg is equal to the mass of the bucket multiplied by the acceleration of gravity, giving us a force of 13.72 newtons. Take a look at all the forces that we've calculated and compare them to the force of gravity in the bucket. This is the explanation of how the water stays in the bucket in one case and not in the other. When the centripetal force exceeds Fg, the water stays in the bucket, which is the case for the first two scenarios. The second scenario's centripetal force is close to Fg, but still more to keep the water in the bucket. The last scenario's centripetal force was below Fg, which causes the water to spill out of the bucket, ultimately in the direction of Fg. The important factor that causes a difference in the forces is the velocity of the spin. As the speed increases, the force will increase. As the speed decreases, so does the force if you compare the proportionality. What is centrifugal force then? It is the force that keeps the water at the bottom of the bucket. It is the force that lures the object away from the direction of rotation, which keeps the water in the bucket. Inertia has to do with this because the water wants to travel in a tangent away from the instantaneous point in a circular path. So when the bucket of water is pulled upwards during the rotation, the water has a tendency to keep traveling in the upward direction, but the force of rotation moves it in a circle. And that is how water magically stays in a bucket even when it is flipped upside down.